Ada Lovelace was a brilliant mathematician, and a woman, no less, who lived in the 19th century. And who is also the muse of my new piece for cello solo. My piece is called A.D.A, or A.D.A, the dots making her name more abstract, because while she is the inspiration, it is not directly a piece about her. And also, since the cello's tuning is A, D, G, C, when I see A.D.A, I always have to think. Ada Lovelace worked together with her fellow mathematician, the Englishman Charles Babbage, who had designed a very cool machine called the differential engine. This was basically the world's first calculator. Now, it was completed in the 1820s, so this machine was cutting edge and it looked awesome. Together, Lovelace and Babbage designed an even more complex machine called the analytical engine that could not only add and subtract, but perform more advanced mathematical operations. Lovelace was way ahead of her time and said that this machine would not only be able to do maths, but also produce language and music. She called her work poetic science. The analytic engine worked with punch cards, basically strong pieces of paper with holes in them that told the machine what to do, much like with a pianola or a music box. To demonstrate the amazing potential of the analytic engine, Lovelace got it to calculate the 9th Bernoulli number. Now, Bernoulli numbers are pretty complicated and still used in some digital security systems even today. I won't go into it in depth, but the first Bernoulli number was discovered by Bernoulli, a mathematician, ages ago. And to calculate the second Bernoulli number, you need the first one. To calculate the third Bernoulli number, you need the second. This is a whole operation. To calculate the fourth, you need the third, etc. So calculating the 9th Bernoulli number is quite an achievement. For the analytic engine to do this, to calculate the 9th Bernoulli number, Lovelace made a series of charts with instructions that told the machine exactly what to do. These charts were called notes, and there was a whole bunch of them, starting from note A to note B, going to note C, and ranging all the way to note G. Note G is the last one that she made, and it is said by many to be the first computer algorithm. In the last movement of my cello solo piece, A.D.A, that is inspired by Ada Lovelace, I reflect on the question, what will the music of the future sound like when we are no longer around to hear it? For example, in the years 23. So for this, I translated note G into music. This is how I did it. So first you need to understand how to read note G. It's not as complicated as it looks. Every step in the calculation process is called an operation. The first column here just gives the order of the operations. So operation 1, 2, 3, etc. The second column tells us something about the nature of the operation. So basically, what do we have to do? In operation 1, you need to multiply. In operation 2, you need to subtract. In operation 3, you have to add. Operation 4, it's not very clear on this printout, but you have to make a division. The third column tells us which variables are used here. So in operation 1, 1v2 multiplied with 1v3. The way the variables look is another thing to understand. If we have 1v2, it means the first form of variable 2. Variable 2 will be changed in some way by these operations, and it will come back later. The second time it comes round, it's called the second form of variable 2. So in operation 1 on note G, what happens is we have the first form of variable 2 times the first form of variable 3. So let's say that, for example, 1v2 equals 2, 1v3 equals 3, then 1v2 times 1v3 will give us the result of 6. Now, this is where it gets clever. The result we get here, the result of operation 1, 6, is attached to certain variables, or, in the words of note G, these variables that you can see in column 4 receive the result of this operation. So that means that here we have, at the end of operation 1, we have 1v4, 1v5, and 1v6. These receive the result of 6. So that tells us these variables equal 6. If we continue then to operation number 2, which is 1v4 minus 1v1, we already know that 1v4 is 6. 1v1, we don't know the value, but the value for 1v1, it was determined by one of the preceding notes, A through F. So, for example, if 1v1, let's say, is 4, then this operation will obviously give us the result of 2. And if we go here to fourth column in note G, the variable receiving the results of operation 2, 2v4, you can see there. That means that operation 2 has told us that 2v4 equals 2. There is a lot more on note G, as you can see, but this is the part that I used for my piece. Operations 1 through 7, columns 1 to 4. Now, if we look at it in a non-mathematical way, a variable can be anything. It can be a number, but it can also be a smiley, or a color, or a melody. Let's call it a series of musical notes. In note G by Lovelace, variables are used to calculate other variables. But there are also variables that you have to know before you start. In the cases of Lovelace's instructions, these variables are calculated in preceding notes A, note A to note F. So when you start with note G, you already need to know the value of these variables. The starting variables, as I call them for myself, are not the result of an operation described on note G. And these starting variables are a little easier to see on this copy I made of the relevant bit of note G. So the starting variables here, 1v2 on 1v3 we need to know before we begin. Here you can see that 1v4, 1v5 and 1v6 receive a result from operation 1. So these are not starting variables. You can just go ahead and cross them out. 1v4, 1v5. Now here we have 1v1, which is not a result of a preceding operation, so that's a starting variable. 1v1 we get again. 2v5 is a result of operation 3, so that can go. 2v4 is a result of operation 2. 1v11 we get from here. 1v2 is a starting variable, but we've already had it. So 0v13, aha, we've not seen it in this column, meaning we need to know its value before we begin. 2v11 comes from there. 1v3 is a starting variable, but we've already had it up there, and 1v1 from there. So you can see that here our starting variables, i.e. the ones that we have to know before we start, are 1v2, 1v3, 1v1 and 0v13. So for my piece I wrote a musical gesture for each of these starting variables. So there is a phrase called 1v2, for example, and there's also a phrase called 1v3, and a phrase called 1v1, and so on. These are my starting variables, and then I proceed according to note G operations in order to produce more pitch material. So now it really becomes interesting, because we can work out the value of, say, 1v4 or melodies that come later on by performing an operation on existing variables, i.e. by processing the melodies I already written in a certain way. There are 4 kinds of operations: adding, subtracting, multiplying, and dividing. Now, how can we use this in a musical way? Anything is possible, but this is what I came up with. To add 2 series of musical notes, you simply combine them. So all the notes stay the same, but you end up with more. We are going to take the theme of the Happy Birthday song and add it up with the beginning of The Swan by Saint-Saëns. So basically we're going to say series 1 plus series 2. Now how you exactly combine the notes is up to you. There's a lot of freedom and creative options in that. But what I'm going to do is take the first note from Happy Birthday, the first 2 notes from The Swan, two notes from Happy Birthday. Well, let's have another one from Happy Birthday. And then, oh, look, this one corresponds. So we've had that one. Then we're going to take 2 notes from this one. And oh look, they were back in Happy Birthday. So we take the next note from Happy Birthday. And then, why not? Let's finish with this one. And I think to make it a little bit more interesting, we're going to move this one to the end. So to make it a bit more clear, these notes are from Happy Birthday. And these notes are from The Swan. And as you see here, I've put them in another octave. That's totally cool. So what we get here then is the result of Happy Birthday plus this one, and it sounds like this. Now you may have noticed that for the rhythm I just did whatever. That's because I decided to do the rhythm myself. You can totally also apply this method to rhythm, which I'm sure would be very interesting, but I decided to use it only for pitch. Subtracting is a little bit less obvious, but what I did was to identify the most frequently occurring interval in series 1 and remove it from series 2. For example, we are going to start with Happy Birthday and we are going to subtract the Marseillaise from that. Now, the Marseillaise is handy because it has a very clear, most frequently occurring interval. Here we have a perfect fourth, and here we have another perfect fourth. So we can say, if we want to just be a bit blunt and simple, that the perfect fourth is the essence of the Marseillaise. If we go back to Happy Birthday, we see that here we have a perfect fourth. So in order to subtract the Marseillaise from Happy Birthday, we are going to get rid of this, which gives us okay, for dividing you have to bend your head just a little bit, but you can imagine that you're dividing sweeties amongst your friends, like so. One more. And in a similar way, you can divide the pitches of series 1 among the rhythm of series 2. For example, if we take this one and we divide it by Super Mario, that means we are going to use the pitches of this one with the rhythm of Super Mario, which, with Apology to Sanson, gives us and finally, to multiply one musical series with another musical series, it gets a bit more technical and a lot more creative. Now for this it's helpful to visualize a keyboard. A semitone is of course one semitone. If we have, let's say, a minor third, pardon the tuning, it's 1, 2, 3 semitones. So a minor third equals 3. A perfect fifth is 1, 2, 3, 4, 5, 6, 7 semitones. So a perfect fifth equals 7. Correspondingly, each interval has a number that is basically the number of semitones inside the interval. So in the case of this example, we have the Swan by Saint-Saëns. Turn this into a row of numbers. We will get semitone, so 1, perfect fifth, 7, perfect fourth is 5, whole tone is 2, perfect fifth again, 7, whole tone 2, whole tone 2, semitone 1. Then we write that row over here on a separate piece of paper. 1, 7, 5, 2, 7, 2, 2, 1. So this is the theme of the Swan. For the second one, we have Tchaikovsky's Nocturne. Minor sixth, so 8. semitones twice. 4, 1, 7, 1, 1, 5. So we write this next to this row here. Now to multiply these rows, we need the same amount of numbers in each row, and as you can see, this one has more. To reduce the amount of numbers, I came up with a few rules. Rule 1 is that any number that occurs twice in a row, optionally one of those may be left out. Now here it's not necessary because this row has fewer numbers, but here we can, for example, delete one of the ones. That already gives us an equal number. To multiply these, we're going to write them neatly next to each other. I also made up the rule that no number can be multiplied by itself. And here we have 2 7s. So what we're basically going to do is we're going to swap these two numbers around. Now if we multiply these, we get the new set of numbers, which is going to be the intervals of the new melody. Now, as 12, the number 12 is an octave, anything that's much bigger than 14 is basically going to be too big an interval for it to still feel like a melody. So here 14 is still acceptable, but for 20 we're just going to subtract 12, which basically makes it an octave lower. So then we have the intervals of the new melody. Let's see what that gives us. As the starting point is this one, we have to start on the same starting note, which is a G. Okay, and then we're going to do 8, 7, 8, 2, 7, 14, 2, 10. And you can use those in any direction you like, whatever sounds best. I decided to do this. From G, we go up 8 semitones, down 7, down 8, up 2, up 7. I thought 14 was too big, so minus 12 is 2, 2, and up 10. Which gives us this cool melody. So in order to keep it neat and understandable, these were all just simple examples. Of course, in real life, or my piece A.D.A, it's a bit more complicated. But if you want to know the ins and outs of that, feel free to analyze it yourself. I hope you enjoyed this as much as I did, and if you have any questions, let me know. And of course, feel free to come to the concert.